Hello, everyone. This is Xingfeng Shao from University of Southern California. Today, I'm going to present a recent study about concurrent laminar CBF, CBV, T2 bolt, and CMRO to fMRI 7 test in human primary motor cortex. Oops. And I have nothing to disclose. For laminar fMRI, if you look at this tiny area of your brain cortex, it contains multiple layers, just like circuits. So layers communicate to each other, and each layer has a different function. So laminar fMRI allows us to study the brain circuits in different brain areas. So in laminar fMRI also requires both high spatial and temporal resolution and also sufficient signal-to-noise ratio. In order to achieve this 1 millimeter isotropic spatial resolution, we propose the zoom 3D grids acquisition to cover a small area of the brain. And also we propose a new labeling strategy compared to conventional ASL labeling here. So we move our labeling plane above the circle of Willis and simultaneously perpendicular to ACA, MC, and PCA. So in this way, we have a better B1 homogeneity, and also the blood flow is slower. So we can achieve high labeling efficiency, about 82%, with a shorter TR, and the SAR is below the 75% of the first level limit. So our ASL study you successfully demonstrate the different laminar CBF increase in human M1 during the finger tipping and the finger brushing tasks. So as we can see, during the finger brushing, only brings the sensory input to the superficial layers. So while during finger tipping, so there's additional sensory input from the premotor area and also generates from the deep layer to generate output to the spinal cord. So here are the resting state finger tipping and finger brushing CBF maps. As you can see, during the finger brushing and the finger tipping, there's a very strong activation during the M1 areas. So in this two zoomed box, we can see during finger tipping, there's a very clear two-peak activation pattern. While during finger brushing, you can see there's only relative smaller response in the superficial layers. So this year, we expanded our ASL sequence to acquire both ASL basal and both contrast. So here's a sequence diagram. So the inflow blood is not inverted during the control ASL condition. So we added a non-invasive HS inversion pause, and so this pause was used to null the background signal and also generate the visual contrast. So due to the limited B1 around the brain and 7 Tesla, we assume the fresh inflow blood only experiences one inversion, and we actually measure the inversion efficiency of this pulse around the whole brain. So we can optimize the post-limit delay about 1160 milliseconds to null the inflow blood signal. So this PLD is also optimal for ASL study because in our previous research, we realized the arterial transit time from the labeling plane to M1 area is about 1 second. So this PLD is slightly longer than our arterial transit time, which can be used to optimize to maximize our ASL signal. So we also acquired the concurrent T2 bolt signal after 500 milliseconds after our ASL acquisition. So here is our acquisition timing. So as you can see, there's an interleaved control and the label acquisitions. And after each of them, there's a bolt acquisition. So the control signal gives you the visual contrast. And we subtract the control and the label to generate the ASL perfusion or the cerebral blood flow contrast. So our spatial we have 14 slices, and our implant resolution is 1 millimeter. So the TR for each CBF or visual image is 24 seconds, and the TR for both image is 12 seconds. So with the CBF, CBV, and the both signal together, we can calculate the CMRO2 signal using some physiological parameter models. So again, for the finger tipping task, we can expect the strong activation in deep and superficial layers. So that correspondingly, we will expect the CBF increase and the visual signal decrease in both deep and superficial layers. So here are, again, the control image show our M1 area and resting state and finger tipping CBF maps. So with the new sequence, we can still see a very strong CBF increase in the M1, S1, SMA, and premotor areas. So here are the 4 zoomed windows showing the signal response in M1 specifically. As you can see here, the absolute CBF increase with finger tipping minus resting state. You can see there's a very clear two-peak pattern during M1 in deep and superficial layers. So this is no smooth at all. This is raw data. So we are very confident about this result. For the bolt response, you can see there's a response dominated in the superficial layers due to the vein contamination. But because we are using the T2 grid bolt, you can still see some response in the deep layers as well. So here is a visual response. As you can see, it's a negative response. And here is after the correction for the bolt contamination. So both of them, you can still see the two-peak activation pattern as well. So here's the laminar profiles of the resting state and the finger tipping activated CBF from the white matter to the CSF. So here's the cortical layers. So here shows the absolute CBF changes and relative CBF changes induced by finger tipping. So you can see the two-peak activation pattern here. So here are the bolt and the visual changes during finger tipping. As you can see, the bolt is dominant in the superficial layers, and the visual has two-peak pattern, but it's negative. So correspondingly, we can calculate the CBV changes from the visual signal. So here's the CBV changes. You can still see the two-peak pattern. Very nice. And here, with all the parameters together, we can calculate the CMRO2 changes. We observed more than 50% changes in deep layers, while there's only about 20% changes in the superficial layers. So more CMRO2 response in deep layers may correspond to higher neuron density in the deep layers. So in conclusion, concurrent CBF, CBV, bolt, and CMRO to fMRI and ultra-high fields opens door to investigating neurovascular coupling in laminar fashion. For more details, please come to my talk on Wednesday in room S11. Thanks for your attention.